To analyze this in further detail, let's consider where our function of x, or our y, is just x squared. This means b is equal to 0, c is equal to 0, and a is equal to 1. Notice that I can rewrite this function as 1 times x minus 0 squared plus 0. So when it comes time to graph it, I know my axis of symmetry is just the y-axis. It's when x is equal to 0, because b is 0. And I know my vertex on this line of symmetry is when y is 0, because c is 0. So this is my vertex, because it's where c lies on the b line. Now in this case, we know a is positive. It opens upward. And whether it's really narrow or really wide, that's all kind of relative, so we don't really know that. I don't know what I'm comparing it to. But let's get an idea of what it looks like. In this case, the best thing to do is to just plug in values. Be sure to label your axes. And now let's try plugging in -2 through 2. So when x is -2, our y is 4. So let's say it's up here. When x is -1, our y is 1. When x is 0, our y is 0. Now this makes sense because this is the point we originally established to be our vertex. And now when x is 1, y is 1, and when x is 2, y is 1/4. I didn't really have to plug in those last three values. I know the vertex is that point I already made, and I also know the axis of symmetry tells me that everything on one side is symmetrical to the other side. So if I could plot the entire left-hand side of this quadratic, I know what the right-hand side looks like without plugging anything in, because it's just symmetrical to the left-hand side about that axis of symmetry. Now let's consider y equals 1/2 x squared. So again, we know the vertex is at 0, the line of symmetry is 0. We know it opens upward because a is positive, it's a positive 1/2. But what does that 1/2 really tell us? Well, let's try graphing this the old-fashioned way. Let's plug in values. So we know the vertex is here, and we know the line of symmetry is there, and it's going to help us. So let's just pick one side, and then we'll just draw the symmetrical version of it. So when x is 1, 1 squared is 1, and 1/2 of that will give us 1/2. Now when x is 2, I have 2 squared, which is 4, and half of 4 is 2. So that goes here. And I know that it'll be symmetrical on the other side, so now I can connect these dots. And notice that it is wider. And it's wider because this smaller a, this 1/2, it's a pretty small number in terms of absolute value. This small 1/2 makes it change not as much. In fact, really, if I've graphed this first y equals x squared, on every single point I can just take half of it and plot that for my 1/2 x squared, because it's just 1/2 of every point on the regular x squared line. So now let's consider y equals 2x squared. Again, we know our origin is the vertex. It's that 0, 0, because b is equal to 0 and c is equal to 0. But now a is equal to 2. So this 2 is positive, so we know it opens upward. And it is a big kind of number. Compared to the 1 and the 1/2 we had before, it's pretty big, so we can expect it to be narrower. But let's just experiment. Let's try it. Let's plug in these values. So when x is 1, my y value is going to be 2. And when x is 2, my y value is going to be 8, which is a really big number. It's all the way up here. So now if I draw the same thing on the other side because of the line of symmetry, and I connect the dots, you can see that this is very narrow, and it changes very dramatically. Because I have such a big a value in terms of absolute value, it's narrow, and it changes very quickly. Note again that I could have just taken my y equals x squared, and on every point, let's say here, negative 2 comma 4, I can just double that y value, because that's all I'm really doing over here. I'm doubling the y value of this original function.